In this demonstration, I will show you how to do a bottleneck analysis of a single bottleneck system. Doing a bottleneck analysis is good for pinpointing which operation or operations that are the bottlenecks. A bottleneck is when the performance of a whole system is limited by one or several objects. It could be machines or material handling systems. Therefore, this system can never reach a higher productivity because of this single machine that is the bottleneck. I will begin to build a simple production system. We'll add a source. I will add a variant called variant A. We'll add this variant to the default flow. I will set the source to produce this variant. Cyclic. And then I will build 10 operations. We'll set the time of the operation to 30 seconds, constant. Availability to 95%. And mean downtime to 5 minutes, 300 seconds. Then I will copy this object. Oh, by the way, I will first name it operation 10. Now I added 10 operations. I will continue to rename them accordingly. 30. Then I will set specific settings on the bottleneck operation, which is operation 40. I will set this to 85% and 10 minutes. I mean time to repair. I will add sync object. Set this to processing time 0. We'll add the buffers, one buffer between each operation. We'll set the buffers to processing time of 30 seconds. Rename them accordingly. I will also set one of the buffers that handles the bottleneck station, which are these buffers. I will set these capacities to 20 instead. And then connect all the objects. So it will be a single flow of product. It will only be variant A that is produced, and really simple production system. Then I'll set the bottleneck station to cycle time of 33 seconds instead. So now, compared to the other operations, this station has a cycle time of 33 seconds and the other ones have 30 seconds. And it has an availability of 85% and others has 95%. We'll start a simulation to see that it works. And the animation clearly shows that it works just fine. Stop, reset, go to experiments, set simulation time of 30 days, warm-up time to 5 days, and replications to 10. And then start experiment. Watch the throughput per hour. It seems to be 87.64 parts per hour. Then we can see if we look at, we can either choose to analyze the buffer levels, or we can look at the utilization of operations. We can use an active period, or we can look at the shift in bottleneck detection. We'll begin with occupation of buffers. As we can see here, there are 3 buffers that are nearly fully occupied, and it is buffer 20, buffer 40, and buffer 30. And when looking at this, you might suspect that the operations after 40 get a lower utilization of their buffers, and therefore maybe operation 40 is the bottleneck. But does it really mean that operation, in this case, does it really mean that operation 10, operation 20, and operation 30 and operation 40 are the bottleneck operations? Well, no. Since the buffer capacities are limited and not infinite, it is not possible to draw that conclusion, although one may suspect that there may be a reason why all the buffers upstreams of operation 40 are highly occupied. But it's also possible to look at the buffer levels over time as a complement to the bottleneck analysis. So you can go to the Simulations tab, and set the values. Set it for 30 days. Log interval time in minutes, 60 minutes. 1 replication should be enough. Start without animation and run the simulation run. Now it's finished. We can go to the graph window and we get this graph. We can look at the different buffers, buffer between before operation 20, 30, 40, 50, 60, 70, 80, 90, and 100. As you can see here, it's quite hard to determine the levels of the buffers. Of course, we can see that operation 20 has a quite long period that it's full. Likewise, operation 30, quite much of the time that it's occupied. Operation 40, likewise the other two buffers, but it's really hard to determine the other buffers. You can see that the buffer level is lower on operation 50. Somehow it's quite high on operation 60 and the other buffers as well. But in order to make this a little bit clearer, you can smooth out this curve and use the moving average window size. So we will use a moving average of, let's say, 5. And we'll look at the buffers again. Operation 20, as you can see, has a limit on a capacity of 5 parts. And as you can see, that it's in the quite high regions here, so it's between around 4 out of 5. And buffer 30 is also quite high, about 4 out of 5. Buffer 40 is a quite high level. The max capacity is 20 parts because of operation 40 is the bottleneck in this case. And this buffer is also quite utilized. Operation 20, however, has capacity of 20, but it isn't utilized that much. And it is because of, even though this buffer will help the bottleneck operation to be able to distribute its finished parts downstream in the line, because of the other operations in the line have a quite high availability of 95% and quite low mean time to repair. This buffer isn't utilized as much as it could. Operation 60, here we can compare against operation 20 and 30, and you can see that it's a lower level on the utilization of this buffer. So by looking at these graphs, you may suspect that, well, somewhere maybe operation 40 or the other operations. Of course, now we know that operation 40 is the bottleneck, but this also shows that on the buffer levels over time that it actually is the case that operation 40 is the bottleneck. However, you can't really say that operation 40 or any other of the operations are the bottleneck because the buffers are limited. So if we would have run this simulation without any limitations on the buffers, we could use this method. But in this case, it can only be complementary information when doing the bottleneck analysis. We can also use utilization bottleneck analysis. If we go back to the experiment, run the experiment again. And we look at the output data. We can go to utilization, and we can see that there's one of the operations that are utilized more than the others. Utilization is actually the amount of working time and setup time of the operation. So the active time that it's actually doing some kind of value adding time to the part. In this case, it's only working time, and it's 80% on operation 40, and operation 20 has 73%, and all the other operations as well, because they have the same settings. So in this case, you would point out that operation 40 is the bottleneck operation. You also can see that it's a quite big difference between these two operations, between 80 and 73%. So it's 7% difference. However, to be completely sure, you should be able to use confidence intervals to make sure that this operation actually is the bottleneck. But there is also another method, and is using active period. Active period means that you add these times, working time, fail time, and setup time, and base your decision on that, because this is actually the active time of the operation, whilst waiting time and block time is only that material isn't supplied to the operation and isn't really part of the bottleneck analysis. In this case, it means that when summing working time and fail time, you will get 95% of the time that operation 40 is the bottleneck operation, or the active period of the operation 40, whilst in the other operations you're about 78%. And this is an even bigger difference compared to utilization analysis. So active period is a quite good way to analyze the bottlenecks. And finally, let's see here, you have the shift and bottleneck detection. The shift and bottleneck detection is the proportion of time the operation has been considered being a bottleneck. The momentary bottleneck is measured for the operations, and an active state is considered to be processing, set up, and failed. This is similar to the active bottleneck. But the thing here is that much of this time that the operation is active is filtered, so only these periods of time that the operation is considered being the bottleneck, the long periods that it has been working or failed or set up, is considered a bottleneck period. And therefore, many of the operations will only get a small amount of time that are considered to be the bottleneck, because at the same time there might be another operation that has a longer active period. I'll try to explain the shift in bottleneck detection in this slide. As you can see here, you have the Gantt chart of 3 machines. An example. In the first period, operation or machine 3 and machine 2 is working. Then they are waiting, doing setup, working, blocked, and so on. You have a break, you have an unplanned period for breaks and shifts. The thing is that when analyzing, when doing utilization analysis, you just add working time, setup time, and just divide that by the total amount of time that the machine has been active. The same thing with the active period, but then you add working time, setup, and failed, and divide this by the time it had been active, in this case for 25 days. The difference with the shift and bottleneck detection is that you sort out these periods that the machine is considered being active. So looking at machine 3, you have this first period that is working, so this period here, then it's considered being active, so it's an active period. And the next period there is not considered being active because it's actually waiting. And then there's a long period that is considered being active, and it's working, failed, working, until there. Then it's blocked, and this period is not considered as an active state, and so on. So you sort out first all of these periods that the machines are considered being active, no matter if it's set up, working, or failed. Just sort this out. And then, in the post-analysis of this data, you set which of these periods are considered being bottleneck periods. So at time 0, you compare them. Which ones of the machines are considered being active? In the first, at time 0, all 3 are active, but machine 1 is considered being the bottleneck period because it has a longer period than the other machines. And therefore, the first period of machine 3 and the first period of machine 2 are discarded. And only this period is considered being a bottleneck. And then go to the end of this period and look which ones of the machines are considered being bottlenecks. Well, first of all, you have a number of machines that are active. Machine 1 is not active after this point, but you have both machine 2 and machine 3. But machine 3 has the longest active period, and therefore this period is selected as the bottleneck period. The time between these periods are called shifting. And the time that it's a sole bottleneck, a single bottleneck, the only bottleneck in the system, is called sole. Once again, at the end of this period, you check which ones of the other machines are active. Machine 2 and machine 1. In this case, machine 1 has the longest active period, and therefore this period is considered being a bottleneck period, and so on. And the result of this is that machine 2 isn't considered being a bottleneck at all, whilst machine 3 and machine 1 are considered being bottlenecks in some way. If we look at this graph, we can see that machine 1 is seen to be a sole bottleneck for 33% of the time, and machine 3 is a sole bottleneck for 39% of the time. Both of them have a shifting bottleneck period of 17%. The strength of this method is actually that this gap between this level here and here are usually bigger than comparing against utilization or the active period alone. So you will, in a better way, be able to determine the bottleneck with a higher confidence interval. So let's go back to the output graph. This bottleneck analysis clearly shows that operation 40 is the bottleneck. In this case, let's see here, it's 81% of the time is considered being a bottleneck. In 46% of the time, it's seemed to be the sole bottleneck. The sole bottleneck means that it's the single bottleneck in the production line. So it's the one and single operation that makes the production, that sets the production rate. So it's considered to be the only and sole bottleneck of the system during this time. So for this whole period of, I think it's 30 days minus 5, so 25 days, 45% of this time is considered to be the single bottleneck of this system, whilst the other percentages here, about 30%, 35, it's considered to be a shifting bottleneck, which means that it's shared among these other operations. So these operations are also considered being bottlenecks, which is also true. But this one has a longer period that is being shared bottleneck with other operations, whilst these operations only are bottlenecks for this particular time. It's about 10% of the time. Some of them are considered to be a sole bottleneck for some percentages, but it's real little. And an important thing to say about this analysis is that the sole bottlenecks are the ones that affect the system quite much, whilst shifting bottlenecks are not that clear. It's hard to say that the reason for it being a shifting bottleneck, but first take care of those operations that has the sole bottlenecks. So if we analyze which is the best bottleneck method, it's always good to do different kinds of bottleneck analysis in order to be sure of the bottleneck analysis. However, the shifting bottleneck analysis gives a good and fairly secure way of determining the bottleneck or bottlenecks of a system. You should always remember that the way you build your simulation model may also affect the bottleneck operations. So be critical about the result. Don't trust the result without carefully analyzing the results.